Hello and welcome back to another VMK in the game development series. In this VMK, we'll be continuing off from our previous video where we implemented the node class. This time we're going to inherit from this node class and implement the node transformation class. And what this transformation class will do is handle all the different kinds of transformations that you'll be allowed to do to objects in your 3D scene. So to get a visual demonstration of what this really means, let's go back into VRealm and take a look. What I've created here is a simple box that has a reference point here in the middle, which is just a cylinder positioned exactly at the center of this box. Now, our transformation node that we're going to be creating will contain a couple parameters. You can change the center, the rotation, the scale, and the translation of your objects. So those are all the different parameters we're going to program in. There are a couple others here inside VRealm, but we're not going to add those in because I find that I rarely use them anyway, so we don't really need them. Now, let's see what each of these do. Let's start off with translation. With translation, you'll have three parameters, x, y, and z. For each of these, you can control how much your object is going to translate. So in other words, how much it's going to move. If we select the x-axis, we can see that as we change the parameter, the box itself translates or slides along the x-axis. Let's reset that. If we change the y value, then it's going to move up and down. And if we change the z, it's going to move in and out of the screen. Oh, sorry, I have both selected here. So z-axis just moves in and out. If we select multiples, then you can see you can imagine you can move anywhere in this 3D space, basically. So that's what translation does. It just moves the object. Scaling, as you may imagine, will scale the object in the appropriate axis. So if we scale along the x-axis, the box itself will appear to get wider, like so. If we scale along the y-axis, it's going to appear like it's getting taller. And if we scale along the z-axis, then the box will appear like it's getting longer. Let me just reset this. So there it is there, getting longer. Okay, so that's scaling. And again, you can scale with multiple axes at the same time, so you can make the box get overall bigger rather than changing the dimensions of it. With rotations, we can rotate about any specific axis. With the first three parameters here, x, y, and z, we need to specify the axis in which the box is going to rotate about. So right now we have selected the z-axis because we have 0, 0, and then 1. Now when we change the rotation value, the box actually changes its orientation along that z-axis. So you can see it there rolling along the z-axis. Let's reset that. If I wanted to twist the box around as if it's like a top spinning on a table, well then I would specify the rotation axis to be the y rather than the z. And then when we change the rotation value now notice that the box spins on its end like so. And if we were to change the spin axis to be about the x-axis, then the box itself will rotate a little bit differently again. This time it's going to roll, like so. So that's how you can control the rotation of the box itself. Now, the rotations can get very complex. Like for instance, once you get multiple axes playing a role in terms of the rotation, then the box itself will all of a sudden appear like it's spinning, relatively complexly. And if you want to keep track of the box in 3D space, keeping track using these parameters can get very confusing. So what we'll do later on is actually implement a different way of doing rotations using quaternions, but for now we're just going to leave it how it is shown here. The way that it's shown here is actually very easy to implement. Using quaternions, it's a little bit extra math, but a lot easier to understand with the numbers. So reset that. So we looked at translation, scale, rotation, and the last thing is the center. Now notice what happens when I change the center. Right by default it's set to 0, so let's change it to be 1. Notice that when I change the value, nothing appears to happen on the screen. Well, that makes sense because currently all the other parameters have been set to be the default values. So just by moving the center location of this box doesn't really do anything to the box itself. So let's set it to be 1. And now let's go back to the rotation. Now if we rotate about Z, notice what happens. The box is no longer rotating about that red circle there in the middle. Instead, it's rotating about a virtual point located here, 1 unit to the right of the circle. Well, what we did with the center is actually we moved the center pivot point from where it was at the center circle here over to the right. And again, you'll notice here that there's the change. Because now we have a rotation with the box, if we go back and change the center point, notice that the box will now begin to move. And it's moving because as we change the pivot point, then the rotation has a different effect. So now you can see the box is rotating about some virtual point located somewhere here over to the right. And again, if we go back to center, we can see I placed it 3.7 units away from this red dot here. And again, you can change the pivot point anywhere you like and have the rotation effect that way. So that's overall how the different parameters work together inside the transformation node. So let's go and implement this now. Oh, there's one other thing I just remembered that I want you to take a look at before we leave here. Let's put the center back at 0. And let's change the rotation back down to 0 as well. Okay, so everything right now is set to its default values. Now notice that the order in which events occur. Let's say we do a translation. Let's say we translate about X, let's say 1 unit or 2 units. And now let's say we go and change the rotation value to be 45 degrees. Everything seems to be okay. We translated it and then we rotated it, right? Let's go reset this. Okay, let's say this time we take the rotation and we rotate by 45 degrees and then we translate. Notice that the translation always happens along the global axis. So in other words, there's an imaginary axis here, X pointing to the right, Y pointing up, Z pointing in. When we translate about that global axis. We don't translate about the local axis, in other words, the axis with respect to the object. So this is important because of the way we're going to implement our node transformation class inside C++. So the order here is very important. If we nest this box, let's go and do that. I'll just create a transformation node here and cut and paste this guy underneath this transform. Okay, and let's change this rotation back to 0. And this translation, rotation is back to 0 and the translation also back to 0. Okay, in this root transform, let's go and rotate the object 45 degrees. Now that it's rotated, using this translation, I can translate the object and notice how it's moving. It's moving horizontally straight across on the screen. Okay, well let's set that to 0. If we go into the nested transform and use this translation, what do you suppose will happen if we translate along the X? Notice it's not moving horizontally. It's now moving on a diagonal. And it's moving on a diagonal because the global rotation axis with respect to this object here, nested, is rotated. And it's rotated because this transform up here rotated it for us. So try to get an understanding of what's going on behind the scenes. This translation and rotation are linked together. And these translation and rotations are linked together, but they will affect one another. So depending on how things are chained together in the scene, the rotation or the translation may behave differently than what you may expect. Even though I'm saying here translate along the X, in terms of the world space, this is no longer the X. This is actually a combination of X and Y. All right, so let's go into C++ now and implement this. To begin, we need to create a CPP file and a .h file. So we'll select our scene.lib and click on New. We'll create a new CPP file. We'll call it node transform. And we'll also do the same thing for the .h. Okay. Node transform itself includes node.h and vector3.h. We need vector3 because we have a couple parameters which have a x, y, and z value. So just to keep things easier and tidier inside this class, we're just going to reuse the vector3 class. Our node transform class is going to be inheriting from our node class, which we created last time. And inside here, we have our constructor and our destructor, and then we have our two function calls, update and render OpenGL. We need to have these, or else this node transform won't compile properly because it is inherited. If you remember back to node.h, located here, we created two virtual functions, and they're virtual because it has the virtual word in front of it, and they're purely virtual because it has equals 0 at the end. So everything that inherits from node has to have these two functions implemented inside it. So node transform has them right here, so we're good. In terms of our member variables, we have a vector3, which contains our translation value. We have another vector3, which contains our center value. And then we have a vector3 for scaling, another vector for the rotation axis, and a floating point number to contain the angle that we wish to rotate about this axis here. And this angle we're going to save as a value in degrees. And that's basically it. So let's go into the CPP file now and implement everything that we need. Okay. At the top, we include stdafx.h and nodetransform.h, and then we have our constructor. Inside of our constructor, we need to define what kind of a node this current node is. So whenever we're doing different kinds of operations from within our scene graph, we may need to do something specific if it's a transform node or if it's a shape node or some other node. Because of this, we're going to reuse this type variable. And again, if we go back to node.h here, you'll remember that we have a node type defined inside node class. So here it is here. And the two different types that we're going to support are the transform type and the shape type. So inside of our node transform constructor, we specify that our type is going to be a transform. Then we initialize our member variables. We don't need to initialize our translate or our center value because by default, whenever we create vector3, the constructor will set the x, y, and z components to 0, 0, 0. And that's exactly what we want our translate value to be, so we just leave that alone. Same thing with center. Our center by default is going to be 0, 0, 0. Our scaling factor, though, we don't want it to be 0, 0, 0, or else all objects that are nested underneath this thing are not going to be visible because they're all going to have a scale of 0. So by default, we want the scaling factor to be 1, 1, 1. So we can do that just by assigning vector3 1, 1, 1 into the scaling member variable. Our rotation axis is not going to contain a specific axis to rotate, but just by convention, it's common to use the z-axis, so I've just chosen here to do the same. So we pass in vector3, 0, 0, and then 1. Just space these out a bit. And we're not going to have any rotation about the z-axis, so I just set the rotate angle to be equal to 0. And that's it for the constructor. You could theoretically set this rotation axis to be 0, 0, 0. However, that may cause problems a little bit later on whenever we do transformations that are nested. So by default, it's better to have a vector inside this rotation axis to point to something. So 0, 0, 1 is just the default we're going to use. The other thing you should realize is it's best to always normalize this rotation axis. So in other words, the length of this vector should always be 1. So if you are rotating about multiple axes, like let's say you wanted to rotate about the x and the y axis at the same time, you could type in 1, 1, 0 here. However, you should really use 0.707 and then 0.707 and then 0. Because if you do that, then the length of this vector will be 1. We'll talk more about that later on as well. Our destructor doesn't have to do any work because we don't allocate any dynamic memory, so it's blank. And then we have our update. Now, our update won't be used for a while, so for now I'm just going to leave it blank and really not talk about it very much. So we'll continue on to the render OpenGL section. Here, what the program has to do is it has to figure out what is the mathematical formula to cause the objects that are nested to rotate according to what I was showing you back in VRealm. Well, the magical formula is T times C times R times S times C inverse. Now, what is TCRS? Well, if you've been paying attention, you can probably figure it out. T is translate, C is center, S is scale, and R is rotate. So in other words, the order of operations that everything happens in is as follows. We first take our object, we're going to translate it, we're going to offset it by the center value, we're then going to rotate it, then we're going to scale the object, and then we're going to move back by the inverse of the center location. So in other words, if our center is 5 units over, we're going to move it 5 units over here when we're at this operation. We're going to rotate everything, and then we're going to move the center back 5 units, so minus 5 here. And you'll see how this works in a second. Okay, here's the magical code to do all the math. Now, node transform itself is going to be a nested transform, as well as it has to work using recursion. Let's talk about recursion for a little bit. Let's go inside PaintShop Pro here and do a little bit of drawing. Let's say we have a node transform here. Let's call it T1, and underneath it we have another transform, and we'll call it T2. Whenever we go and call render, we're going to call render for this guy here. So this guy here will have to go and render itself, but then it has to recursively call the render OpenGL function for everything else inside the scene. Actually, let's make this a little bit more detailed and add some extra nodes in here. We'll add T3 down here. Well, for OpenGL to render everything here, all I've given it is the first point, which was T1. So the way we're going to handle this is we're going to go and render T1, and then we're going to see, okay, is there anything nested underneath us? If there is, let's go underneath us and render it. After we're done with all the children, we'll then say, okay, is there anything next to us? So in other words, down at the same level. If there is, go and render it. After doing all that, then we just say return from our render function. And by doing that, we are guaranteed that the recursive call is going to render everything inside of our scene. Because what's going to happen is we're going to start here. We're going to say, okay, is there anything inside us? We'll go inside here, and then we're going to ask the question again, is there anything inside us? We're going to say, no, there isn't. Is there anything next to us? No, there isn't. So then we return. When we return, we come back to this point, at which point we again ask, is there anything beside us? So we're going to go down here, render this guy, and again, we ask our questions, is there anything inside us? No. Is there anything beside us? No. And then we complete. So in other words, everything gets traversed, or everything gets rendered inside of our scene just by using that logic. Now, it's recursive because the function we call to render this guy is going to call the exact same function. Or in other words, it's going to call itself. But you have to be careful because when you call itself, you're not calling itself for the same point, or in other words, for the same node. If you did that, your program would run indefinitely and it would never stop because it would just keep calling itself and itself would keep repeating the process and it would never end. So you have to make sure that whenever you create recursive calls, the recursion has a stop termination condition as well as a way to propagate forward. So for us, what we're doing is we're calling the render call for this guy, but then when we call the render call again, we call it for some other node. And we always check to see if there's children first, and then we check to see if there's other parents at the same level. So let's see how this is implemented. We go inside the render OpenGL function, and first thing we do, as I said before, is check to see if we have any children. If we have children, then mpin, which is one of the inherited members from node, is going to be valid. So if it's valid, we do some work. After we do all that work, then we go and check to see if we have any MP next members associated with us. If we do, we go and do some work. After that, we just return because there's nothing else for us to do. So now let's take a look at the work that we're doing. Inside here, if there is something nested below us, then we need to take the current value of the model view matrix and push it onto a stack. And what this is going to do is allow us to save the current state of the model view matrix. And OpenGL, by default, I think has 64 different values that it can save on top of its stack. So in other words, you can do this 64 times and be confident that when you return, you'll still have all those 64 members. If you go beyond that, I think you'll either, well, I don't really know what's going to happen. I've never really tried it. But in other words, don't do it, or else your program won't work. So we push the model view matrix onto the stack. Then we go and we call GL translate F by the negative value of the center. So we translate by negative x, negative y, and negative z of the center. Notice we're doing this operation first. Then we go and scale the object, so we call GL scale F by the x, y, and z values stored inside scale. So we're doing this. Then we go and call rotate. So we call GL rotate F. We pass in the rotation angle under the first parameter, and then we have the x, y, and z axis for the rotation here. So we're doing this. Next, we're going to move back to the center. So we again call GL translate F, and this time we're passing the positive value of the center, x, y, and z. And then lastly, we have the translation to take care of. So we call GL translate again, and this time we take the translation x, y, and z. That's basically the magic formula. If you get the magic formula and done in this order, you'll get all the appropriate nested transformations done for you automatically by OpenGL. After doing all of that, we then go and move down inside the tree. So in other words, we go and recursively call render OpenGL. But notice now that we're doing it for the member or the node that is nested underneath us. So we're using the nested node's pointer value to call render OpenGL. Lastly, after we're done with everything inside of the children, we then have to pop the model view matrix off of our stack and save it inside the model view matrix value. So we do that by calling GL matrix mode, model view, and then we go GL pop matrix. So in other words, this pushes it onto the stack, this pops it off the stack, and then this does the special transformation, and here we go and call ourselves recursively. So that's all that is really getting done inside this first part. The second part, if we do have something next to us, again, we call ourselves recursively, so we go and call the next values render OpenGL. Now notice we don't have to do these translations here, and rotations and scales and things like that, because we're not being nested. So we only do that whenever we're nesting ourselves. In other words, well, let's go back into our example here. If we're located at this transformation node, well, we call a render call. So what we want to do is we want to, rotate, translate, scale, everything that's stored inside this guy. We save our model view matrix state before we do any of the translations. So we first save it, we do all the translations according to this, and then we go inside of the children. When we're inside here, we then can go and save the model view matrix again, and then apply all these transformations, and then we go inside of the children. So again, we'll go into here. We then go and we haven't talked about the shape node, but inside here, we would then go and render the object. When we're done, we're going to come back to here. So we need to have our model view matrix back to how it was whenever it was in this state. And then when we're done that, we'll go back to this state here. Now, that may not make too much sense right now because we don't have other objects nested. But for instance, let's say under this child, we had another object like so. Well, we want to render this box and we want to render this cone according to these transformations. But the way that the algorithm is going to work is as follows. It's going to go into here, into this transform, apply the transformation matrix. It's going to go into the box, apply this transformation matrix, and it's going to go inside this shape and render. Well, now, when we want to render this cone, the algorithm itself is going to push itself back over to here, but when it does that, we want to lose this transformation because we don't want to have this transformation affect this shape. So we get rid of that, and we have to reload whatever was saved here. When we have that value, we then can go and apply this transformation. So everything gets nested accordingly. And that nesting is done by using this push and pop mechanism. Okay, so there you go. That's the node transform technique. And I think that's all I wanted to say. I do pass a parameter here, Boolean, which is just render solid. I'm not going to talk about this now. I'll talk about this later whenever we have everything finished and implemented, and it'll make a lot more sense on why I have this. You do have to pass it into all of our nested render calls because they are nested, and they do need the exact same parameters that this one needs because they're all exactly the same function. However, what they do you won't see until we implement the shape node a little bit later, which is actually coming in the next video tutorial. So that's it for now. If you find my videos helpful and you'd like to support my website, please go to www.maticnodes.com and click on the PayPal icon. If you have any questions or comments or would like to have any requests come in, so you want to have something specific done for the videos, drop me an email and I'll be happy to help you out.